Right.
Recording in progress.
Okay, welcome everybody. This is Carlotta's talk, more or less the end of the first year PhD talk, study of a Lotka Volterra dynamics with random carrying capacities.
So, hi everybody, I'm Carlo, and today we're going to talk about Lotka Volterra dynamics with random carrying capacities. Before diving into the model, I'm gonna explain a little bit what's behind. So the first question that you may ask yourself is, what is a Lotka Volterra dynamics? Well, a Lotka Volterra dynamics is a set of differential equations that basically describe the dynamics of species in an ecosystem. The most famous example of Lotka Volterra dynamics is the prey-predator Lotka Volterra equations, but these are not the equation I'm going to be talking about today. Today, to introduce my model, I'm going to first focus on the generalized form of the Lotka Volterra equations. Why? Because basically it has all the parameters that I need to introduce for you to understand my model. So basically, xi is the most important quantity because it's the population of species I times t. Xi dot basically tells us how the species evolve over time. Ri is the growth rate of species I, so basically is the speed at which our species grows if there's nothing stopping it around. Ki is the carrying capacity of the species. The carrying capacity is basically the maximum abundance a species can reach in a certain ecosystem. And alpha ij is the interaction between a species I and a species j. Basically, it tells us how different species interact and what is the strength of the interaction. Can be positive, so the species interact in a cooperative way, or can be negative, so there's competition between species. So once I introduce the general form of the Lotka Volterra model, I can dive into my Lotka Volterra model. So basically is the same as the equation as I've presented before. The only thing that changes is that the growth rate has been put all equal to 1 for all species. So some important things to point out is that alpha ej are Gaussian interaction coefficients and ki are carrying capacities, as I said before, but are random variables, so are drawn from a random distribution. Now you may ask yourself, okay, but why do we draw this from a random distribution? And I have two answers for you. So the first one would be because it introduced heterogeneity, and introducing heterogeneity, it makes the model more realistic. So it means that I can apply it to real ecosystems, but is this true? Well, not really. We all know that the Lotka Volterra equations are not really used to describe real ecosystem. They're far from something real. So the real reason why we're doing this is, well, why not? Could be interesting. So before going on, I want to focus a little bit on why the interaction coefficients are Gaussian. In order to do so, I'm gonna recap a little bit of history about the Lotka Volterra model and the Lotka Volterra studies. So we start from 1972, in which Robert May was the first one to introduce the fact that these interaction coefficients are Gaussian. Why did he do so? Because these Gaussian interaction, these Lotka Volterra equation basically are characterized by high dimensionality. So instead of studying the single interaction that take place between species, it seemed more easy and more helpful to instead characterize those with a specific probability distribution. This allows to apply methods of statistical physics, such as mean field theory, to the Lotka Volterra equations. And in this way, we can gain information about macroscopic quantities and statistical physics averages. So this is the ground from when we are starting. Then, in 2012, Alezin and Tang expanded this theory. They said, okay, but why just Gaussian interaction coefficient? We can look also at other distributions. So this is basically what they did. They did other important contributions as they saw that the stability of a system depends on the type of interaction that takes place. So if the interaction is cooperative, if there's a predator-prey Lotka Volterra model, if it is competitive. Specifically, it saw that prey-predator model are way more stable than competitive one, and that the stability depends also on the symmetry or asymmetry of the interaction coefficients. So if the interaction coefficients are symmetric, actually the stability of the system is lower with respect to the case in which the interaction coefficients are asymmetric. Lastly, the two contributions I want to talk about for this theory is the contribution from Guy Buning in 2017 and the contribution from Tobias Galla in 2018. So what Guy Buning did is that up until this moment, they just analyzed the system in the stable phase, and he asked to himself, okay, but why stop to the stable phase? So he analyzed the entire phases of the system, and he actually discovered that as the interaction strength grows, some phase transitions appear in the model. What instead Tobias did is to better explain the role of stochasticity in Lotka Volterra equation, and also he connected the Lotka Volterra models to evolutionary game theory. So once we did a kind of recap of all the history behind these interaction coefficients, I can go back to my Lotka Volterra equations. So I introduced my equation, but now there's a problem because, as I said before, Lotka Volterra are characterized by high dimensionality. So are difficult to analyze also because they involve non-linear interactions. So what is the solution? Well, the two solutions are kind of consequential to each other, because the first idea is to derive an effective single species process. And with this effective single species process, what we want to do is, like, the final goal of the theoretical part of the study is to find a system involving macroscopic quantities through which I can determine the general behavior of my system. How do I do this? Well, using generating functional analysis. Before diving into generating functional analysis, I want to explain a little bit better what effective single species process mean, because the name could be confusing, but basically what is a mean field approximation, but apply to a Lotka Volterra system. I think we all know about mean field approximation. It has been introduced to all of us via the Ising model. The general idea is that we have an Ising model, we have a spin that interacts with all its nearest neighbor, we have an Hamiltonian with an interaction term. So at the mathematical level, what we do is that we neglect the second order terms in the interaction of the spin variables. And we approximate the single interaction with an average field. So we just take into consideration the average field that the spin we are considering feels because of the interaction with all its nearest neighbors. We can basically use this idea and apply it to Lotka Volterra systems. So what is a Lotka Volterra system? Basically is a network in which species interact with each other. we can take into consideration a species xi. This species xi interacts with all the n species through which it is connected. We have an interaction term that involves a sum. The idea that is behind the mean field theory applied to this system is that instead of studying the sum, we reduce this sum to an average quantity that represents the average interaction that the single species have with all the other species to which it is connected. So, and this is basically these last equations that we have is what we define as a single species, an effective single species problem. And this is for the general idea, but is this actually what we use in our system? Well, no, for the simple reason that my system depends on time. And what I did now doesn't involve a time dependency. What we want to do is instead to apply dynamical mean field theory, which is basically the same idea behind mean field theory. The only thing is that it can be extended, this idea, in order to include cases in which the system evolves dynamically. And so the fluctuations and the interaction do not remain constant over time, but change over time. And we want to include this in our average process that we find. So our equation becomes something that depends on time. And what before was our average interaction term becomes something that depends on time. G of t is the term that is our memory term that takes into account all the previous interaction of the average species with the rest of the population. And eta of t represents a random noise term. Now that I better explained what a single species, effective single species process is, I can go back to generating functional analysis, which is the tool we are going to use to arrive basically to this equation. So what is generating functional analysis? I'm going to make it brief because it doesn't really make sense that I show you long, complicated equations. So the main idea between generating functional in stochastic processes, generating functional is just an object that contains all correlation functions or our stochastic process. If we know the generating functional, we know all the moments. If we know all the moments, we can fully determine the distribution. What is the generating functional in a dynamical system is an object that allows us to compute statistical averages over the trajectories of the system. So what does this mean? Is an object that eventually will lead to the effective single species process that we are looking for. The general idea, to make it as simple and explicative as possible, is that we actually build the generating functional of our stochastic process, where the stochastic process in our case is the Lotka Volterra dynamics. And once we build the generating functional, what we do is that we derive some self-consistent equations via saddle point approximations. What are these self-consistent equations? Again, the effective single species process we are looking for. So this, in the end, from all approximation, generating functional theory, saddle point approximation, and averaging over noise and stuff, in the end, we get to this equation. So this equation basically is what I've introduced up until now conceptually. So it basically tells me how the average species evolve over time. What is the interaction that comes from the rest of the species over time? This is a term that represents the mean abundance of the population. Eta is the correlation term, whereas H is the auxiliary field we basically use to gain information about the system. Instead, together with this effective process, I gain information also over M, C, and G. These M, C, and G are microscopic quantities. In the specific, they are the average abundance of the population, the correlation term, the response function.
The scale X is related to the current capacity.
Sì.
So there is no single species, one representative species.
For every value of the carrying capacity that can be drawn from the distribution that I'm considering. Which, by the way, in this study, you will see only results coming from a uniform distribution, because for the moment is the only distribution we explored. So going back to our process, at this point, you may think, okay, but you didn't really reduce the complexity. Like, this is still a complex equation. But what can we do now? We can see that this basically is a self-consistent equation. Why? Well, because the x of t is defined through g, m, and eta, and m, c, and g are defined through x of t. So we can solve this problem. How do we do it? We start from an initial guess for these quantities. Using this initial guess, we are able to generate eta. Once we have eta, we basically have all the quantities that are inside this equation. So we are able to generate x of t. But once we have x of t, we actually can reevaluate once again these quantities. So we obtain new values for these quantities, and basically we repeat the process all over until we reach convergence. We are almost at the end of our theoretical study. So once we have our effective process, we have the equations for the macroscopic quantities, we have the self-consistent problem, we may ask ourselves, okay, what now? See? Should I go back?
What is not on the slide is that the C is here written as correlator of X. It is also the correlator of E. That's a crucial element of that self-consistent problem.
I didn't say it.
Maybe you said it.
Okay.
For the X, for the people who.
Sorry.
Maybe you said.
Okay. Going back to our final step of the theoretical study, we got all that information. Still, it's not enough to find our system of cute, simple equations from which we can draw all the quantities that we want. So what we do is that we use the fixed point assumption. What we say is that, okay, we are at this point. Now, I say that my system at a certain point reaches a stationary state where the stationary state do not depend from the initial conditions. This, of course, modifies the quantities M, C, and G. C becomes a constant. G does not depend from G now depends only of time differences. So we are at the point in which we are actually able to find the famous system of equations that we wanted. I'm not going to write here the system of equations. I'm just going to say what the macroscopic quantities we care about are. So we have M, which is the mean abundance of the population, of the mean abundance of a species in the population. K, which is the response function to perturbations. Phi, which is the fraction of surviving species. Sigma square, which is the variance of the interaction, so the strength of the interaction. And mu, which is the mean of the interaction. Are fixed parameters. well, are fixed, but we study yes, but the idea is that we study this variable as a function of these parameters. So now, done with the theory, we go to numerical results. The first thing that we did was actually to see, okay, we found this system of equation. Does it work? And yes, it does. We checked it for phi and m, so the fraction of surviving species and the mean abundance, where the lines are the theory, whereas the dots are the simulation of the Lotka Volterra dynamics. We can notice, I think we can notice from these plots is that I'm gonna say what is gamma. So basically gamma, what it does, it's gamma is the covariance of the interaction coefficient. What does it mean? It means that a negative gamma is telling us that the interaction between species is competitive. A positive gamma tells us the interaction between species is mutualistic. So what we can see from this is cooperative, basically. What we can see from this plot is that actually the fraction of surviving species as a function of the strength of the... What did I do? Okay. What happens is that the fraction of surviving species as a function of the strength of the interaction is actually bigger for a competitive system, whereas it goes decreasing for cooperative ones. From this other plot, we can see instead that the mean abundance, even though the fraction of surviving species is bigger for competitive systems, the mean abundance of the species for competitive systems is actually smaller with respect to cooperative ones. So this is the first check that we did. Then, given that we are focusing on the case in which we draw the carrying capacity from a random distribution, we thought, okay, let's see what happens when we study these two quantities, but we study these quantities for specific values of the carrying capacity that I've drawn. Want to specify here that, as I said before, we draw carrying capacity from a uniform distribution and from values that are distributed between 0.5 and 1.5. So basically it's a uniform distribution centered in 1. What we see from this plot, we studied these quantities for different value of the interaction strength. And what we see from this plot, as we expected, is that bigger carrying capacities imply a bigger fraction of surviving species. Why? Well, because a bigger carrying capacity give an advantage to the species with respect to all the other ones. So it basically behaves how we thought he would behave. And same with the mean abundance, a bigger value of the carrying capacity implies a bigger mean abundance. You may notice here that actually the last two values for the interaction strength do not behave as expected from the theory. We're gonna go back to this in a while. Left behind the check if the theory work for the dynamical system. It looks like it does, so we try to gain information about the species abundances, the species abundance distribution, P of X. So from numerical study, the theoretical distribution basically is a mixture of Gaussian. We studied numerically the behavior of the system, and we saw that the numerical data are in agreement with our theoretical expectancies. Going on, really important, we study the phase diagram. So what is the phase diagram? Basically, the phase diagram is the diagram that tells us when the approximation of a fixed point is valid for our system and when it's not valid anymore. What does this mean? It means that this system behaves in a nice way only for certain sigma squared mu parameters. Then if we exceed certain values, the system behaves unexpectedly and all the approximations, all the evaluations done until now do not work anymore. So there are two main sources of instability in our system. The first one comes from the fact that we have diverging solution. So to find these lines, we basically saw when the mean abundance M exploded, which means, and through this, we were able to identify the mu and sigma values on the plane that lead to this divergence. A nice thing that we were able to see from this study is that I say again to you, we are now in the case in which we are drawing carrying capacity from a uniform distribution in an interval between 0.5 and 1.5 centered in 1. What we saw is that the phase diagram in the case of divergent solution is the same for this distribution. So for the case k equal to 1, where k is the difference between the maximum value we're drawing from, 1.5, and the minimum one, 0.1. So the phase diagram for the divergent solution is the same between the case k equal to 1 and k equal to 0. So if we have carrying capacity draw from a random distribution centered in 1, or if we have all carrying capacity for all the species of the system equal to 1, basically the phase diagram when M goes to infinity is completely identical. The second source of instability of our system comes from, well, we performed the linear instability analysis to find the other source of instability from our system, and we were able to find, like, these striped lines are the lines that represent our linear the lines over which we reach linear instability. Why I put in here these dotted lines is because below the striped lines, we have our system reaches a fixed point. Above the striped line, but below the dotted lines, the system is in a multiple fixed point state. And above this case, the system does whatever it wants. And the interesting thing, like at a first glimpse, when we first found this phase diagram, it looked like nothing changed from the case k equal to 1 and big K equal to 1 and K equal to 0, so that nothing changed from the Lotka Volterra system in which all the carrying capacities are equal to 1. Then going a little bit more in depth with this study, we actually saw that this being, I here show only the case for gamma equal to minus 0.2, but basically is the same type of behavior for all the gamma that we study. We actually see that this one being the line coming from the case in which all the carrying capacities are equal to 1. When we increase the length of the interval from which we are drawing our carrying capacity, the difference between these two lines in the phase diagram increases. And now that we arrived at this point, you may ask me, okay, Carlo, but before there was a plot that wasn't really working. Why is that? Well, that plot even though I didn't write it. Why? Because I forgot. It was a plot in the case of, if I'm not mistaken, gamma equal to minus 0.2. And we can see that the line, the instability line for gamma, for this value of gamma is around 3 point something. So we can go back to our previous graph, and we see that for the two values in which the theory does not correspond with the numerical simulations, the strength of the interaction is above the linear instability values. So basically at that point, we really don't care what the system does because all the approximation that we did up until now are not working anymore. And going back to the phase diagram, well, that's it. Now we want to, I will explain to you what we aim to do because that is the phase diagram, but does it work? Well, we haven't checked it yet because the one that I show it to you are just theoretical values. What we want to do now is basically the same that we did in the case in which I showed to you the P and M as a function of sigma squared, where I compare theoretical values to numerical ones. The idea to compare to numerical ones here to see if the system actually reaches instability for the values we predicted is to look at the spectrum of the reduced interaction matrix to check the validity of the phase diagram. And as I said before, up until now, our study was only on a uniform distribution. We want to see what happens if instead of using a uniform distribution, we draw our carrying capacity from a delta distributed, from a delta distribution with 2 peaks. So basically we have just 2 values of carrying capacities in all our ecosystem, but each carrying capacity has a certain weight. So we see what happens when the weight of a certain value changes with respect to the other. And that's it.
Cool. Are there any questions?
I want to understand it.
Yes, in the dynamical mean field equations, so there's an equation for every species with a fixed carrying capacity, but the averages are taking over all the possible case. Is this the?
What should I
You have the dynamical equations.
This one?
Yes. So the averages are over what?
The averages are over all the possible realization of the interaction matrix and over all the possible k values.
Focus of consistent equations compared to numerical different dynamics.
Way faster. Well, the idea is that to have a grasp of how a real ecosystem works, real ecosystem, not really, but the idea is that ecosystems are characterized by a huge number of species. So imagine we have 100 species, which is an even low number. This means that our interaction matrix is 100 times 100. And to numerically simulate all of this is really, really heavy. Like,
But here, if you have like one carrying capacity for each species, you need to solve how many of these self-consistent equations. So I'm wondering.
But in the end, we don't even use the self-consistent equations. That's
We
the
don't?
idea, because
Okay.
the self-consistent equation is just a intermediate step to arrive to what we really use in the end, which is the equations for the microscopic quantities.
Oh, so you don't actually solve them for
No.
four. Okay, that's nice. Yeah, I didn't get that. Thanks. Yeah. Yes.
Make a fixed point.
Yeah.
And you will on paper pen it in but you don't actually pay. There are methods for this. Generate trajectories from this. For the alpha, that's what I was.
Sì. Sì, sì.
But then what is the capital gamma? Because
What is gamma?
I don't think yes.
Gamma is the covariance of the interaction coefficients. So if gamma is negative, it means that we have competitive interaction. Positive, we have cooperative interaction, like a positive interaction with it. Species help each other.
Not be even by the so because the parameters are sigma, but
Also gamma. Because mu is basically the average value. Mu divided by m is the average value of the interaction coefficients. Gamma squared divided by n is the variance. Sigma squared divided by n is the variance. Gamma is the covariance.
alpha ij and alpha j. So you have to switch it and if I acts on j and j acts on j, you have two coefficients. You can use the covariance between these two coefficients. If that is positive, then basically the two alphas have the same sign. So I benefit from you benefit from you. Or I effectively make it and you effectively make it. This is the answer for gamma. We don't discuss it's positive. I need you. And so I do harm to you, but you don't from me. So gamma minus one means you have lots of favorite things. But when gamma negative, it's not competitive, it's competitive.
It's competitive.
It's not correct. It's not straight or correct,
With competitive, I meant like one has one side, like one gains from the death of the other.
What you cannot distinguish with this approach is the competitive competition you can.
But it's just maybe, but shouldn't it be like for every pair of mu and sigma you have not because you are drawing the alphas from them, should be a gamma given by that. I don't see how it's in useful.
No, I didn't. But I can do it on the blackboard. Okay.
How do you do those? And the question is, can you predict the results with the matrix formulation? Or they just push? I remember from that paper, they also have the mu sigma and then the covariance. You get all the predictions for what will the study. You go further.
Do I? No, your question is clear. I don't know if I know the answer. Well, from that, what I grasp from what they did is that they could predict the stability based on the type of interaction, and if the interaction is symmetric, the system is less stable. But this is fraction of surviving species. So I really don't know really. Sì. Sì.
This is a very complicated. Joe Barry and I started asking us studying the book, and we go to this 3 years, and then we can really this is more than 2 years. There is an answer, yes, but